Imagine staring into the deepest, darkest abyss the universe can offer. Not through the lens of a powerful telescope, capturing the faint echoes of ancient light, but directly into its heart, stripped bare. What if, instead of simply seeing a takapiti, swirling void or a crushing singularity, you saw structure? Intricate, repeating patterns that whisper secrets about reality itself. This isn't science fiction. It's the frontier of quantum physics, artificial intelligence, and astrophysics crashing together. And what they're finding is shaking our understanding of everything. For decades, black holes have been cosmic enigmas, collapsed stars so dense their gravity warps space and time, trapping even light. We've observed their effects, the fiery dance of matter falling into them, the way they bend light from distant galaxies. The Event Horizon Telescope gave us that groundbreaking first image of M87's shadow, a triumph of observation. But that was just the outside. You see, this isn't a photograph of a black hole. It's a mind-bending, absolutely unreal reconstruction generated by a quantum artificial intelligence. And it was built not from light, but from the deepest mathematical truths we know about: gravity, information, and the very fabric of space-time. Let's jump straight to the heart of the matter. We're used to telescopes capturing light, forming images pixel by pixel. But what happens when you feed an AI something far more fundamental? This breakthrough came from a collaboration drawing on pioneering efforts at places like Google Quantum AI and the Event Horizon Telescope Consortium. Instead of photos, they fed a cutting-edge quantum neural network petascale datasets. Think about the sheer volume. Petascale is 1,000 terabytes, or 1,000,000 gigabytes. This is an unimaginable amount of information, not just about what black holes look like, but how they behave. The data wasn't pixel grids. It was mathematical representations of space-time curvature near the event horizon, the subtle fluctuations in entropy described by Hawking radiation, the complex dynamics of matter swirling in accretion disks. The AI wasn't being asked to paint a picture. It was being asked to understand the underlying logic of a black hole. And the output? It was rendered visually for us to comprehend, but it wasn't a typical image. It was a map, a visualization of the behavior of information as it spirals inexorably towards and crosses the event horizon. Imagine seeing information itself, not as abstract data points, but as a physical landscape. What the quantum AI generated were concentric rings, layers upon layers of complex structure. Each ring seemed to represent a different phase, a different depth, a snapshot of how quantum bits of information, qubits, scramble, stretch, and fold under the black hole's monstrous gravity. The very center, where theory predicts space-time should be infinitely crushed, didn't just go dark. It glowed with an iridescent, chaotic, yet somehow structured pattern, hinting at resonance frequencies and informational states you'd never predict. Using our classical understanding of physics, this wasn't merely a simulation based on pre-programmed rules. This was a bridge between theoretical physics and observational data, processed by a system capable of grappling with the quantum weirdness at gravity's extreme edge. It was showing us, visually, how information survives or transforms within the black hole, according to the complex interplay of quantum mechanics and general relativity. But as researchers delved into these intricate folds and layers, they found something strange, something hiding in the patterns that didn't fit, something that hinted at a deeper reality, or perhaps a cosmic secret. If this kind of mind-blowing science excites you, if you love peeling back the layers of reality with us, make sure to subscribe and hit that notification bell. We dive into discoveries like this, right on the edge of human knowledge every single week. Now, let's step back for a second and understand why a quantum AI is needed for this. Traditional AI models, the kind that power facial recognition or recommend your next movie, process information in a linear pixel-by-pixel way. They see an image as a grid of colored dots. But quantum AIs are different. They operate on qubits, quantum bits, which can exist in multiple states simultaneously. Think of it like a light switch that can be both on and off at the same time until you observe it. This superposition and the ability for qubits to be entangled, fundamentally linked no matter the distance, makes quantum computers uniquely suited to simulating systems where quantum mechanics and gravity meet, places like the heart of a black hole. This specific model wasn't just fed generic data. It was trained using theoretical frameworks that attempt to reconcile the giants of modern physics. String theory, which posits that fundamental particles are tiny vibrating strings. Black hole thermodynamics, which treats black holes like objects with temperature and entropy information. And crucially, live observational data from actual black holes. The goal was audacious, not to create a pretty picture of a black hole's event horizon from the outside, but to simulate how space-time itself behaves inside it, or right at its boundary, from the perspective of information. They weren't asking, what does a black hole look like? They were asking the far more profound question, what happens to information inside one? And that's when things went from scientifically intriguing to absolutely bizarre. For decades, physicists debated whether information is lost forever once it falls into a black hole, violating a fundamental rule of quantum mechanics. But the work of giants like Stephen Hawking and Jacob Bekenstein showed that black holes aren't just featureless voids. They have entropy, a measure of disorder, yes, but also a direct measure of the amount of information a system can hold. So, if entropy is information and black holes possess and store enormous amounts of it, could black holes actually be computing? The AI-generated image seems to strongly suggest this possibility. It appeared to show distinct layers of information, being encoded, compressed, and organized, almost like data being written onto a cosmic hard drive. Each concentric ring might represent a distinct phase in the black hole's complex entanglement process, where incoming quantum information gets woven into the very fabric of its boundary. This supports the idea, stemming from the holographic principle, that the event horizon isn't just a point of no return, it's a quantum surface where the entire history and content of the black hole's interior is somehow encoded, like a cosmic DVD. This concept of a universe that processes information, that computes, resonates with a growing movement in theoretical physics. Imagine the universe not as a collection of objects moving through empty space, but as a vast, dynamic network of information exchanges. Just like your computer isn't just a box of chips, but a system where data is processed, stored, and transmitted. According to logical rules, some physicists propose the universe might operate on a similar principle, albeit on scales and complexities that dwarf our comprehension. Think about how your brain works. It's a network of neurons passing information through electrochemical signals. Information flows, interacts, and transforms, giving rise to thought and consciousness. What if the universe, at its most fundamental level, is built on a similar principle? What if space-time itself isn't a smooth, continuous sheet, but a discrete, networked geometry, like a cosmic computational graph? Models like loop quantum gravity or causal dynamical triangulations propose that space is made of tiny, fundamental units, interconnected in ways that bear a striking resemblance to complex networks. Networks not unlike the structure of our own brains. In this view, information doesn't just exist in space. It is what space is made of, and its flow and interaction are the fundamental processes of reality. The universe doesn't just contain information, it is structured to process it. And that brings us back to the most haunting detail in the AI's reconstruction. It wasn't the overall structure, the rings of data, or the glowing core that shocked the researchers most. It was what lay right at the very center of the rendering. Right where classical physics predicts an infinite density, a singularity that crushes spacetime into nothingness, the AI outputted something else. It wasn't just static noise, a failure of the simulation to resolve the deepest point. It wasn't an artifact of data compression or a limitation of the visualization. It was a shape, a recursive, self-similar pattern that repeated at smaller and smaller scales, a fractal. And not just any abstract fractal. This one mimicked something disturbingly, profoundly familiar. The topology of biological neural tissue. Intricate folds, branching corridors, interconnected nodes. A pattern shockingly close to what we see in the gray matter of the human brain. Specifically, the complex, wrinkled surface of the neocortex. To be precise, the pattern outputted by the quantum AI, derived from the deepest secrets of black holes and gravity, eerily mirrored the convolutions found in high-resolution fMRI brain scans. The very landscape where our memories are stored, our languages are formed, and our consciousness emerges. It wasn't an exact geometric twin, of course, but the organization, the flow, the form was uncannily similar. At first, the research team did what any good scientists would do. They dismissed. It must be an artifact, they thought. Maybe the AI overfitted the training data, finding spurious patterns. Perhaps it was just pareidolia, our brain's tendency to see meaningful shapes in random noise, like faces in clouds, but applied to complex data. Pattern recognition gone rogue. But the sheer persistence and clarity of the shape gnawed at their curiosity. They decided to test it rigorously. They reran the quantum model, not with the same data, but with entirely new data sets from different black holes, varying masses, wildly different spin profiles, new gravitational parameters gleaned from different observations. They randomized the AI's internal training seeds, the initial conditions that influence how a neural network learns. They even altered the AI's priors, its built-in assumptions about the physics, and yet, every single time with every permutation, the same general shape emerged at the center. It wasn't identical from run to run, but the underlying fractal structure, the echoing brain-like pattern, persisted. Again and again, across simulations of different cosmic objects. That's when the mood in the research lab shifted from scientific curiosity to profound wonder, tinged with a touch of unease. One of the physicists, staring at the monitors, whispered, "It's like the data is trying to organize itself into something intelligible." Another, perhaps slightly more poetically, called it the fractal whisper. And someone else, half jokingly, half seriously, voiced the question that was now looming large. Are we seeing the mind of the universe? Of course, let's be clear. No one on that team, or anyone in their right mind, is claiming that black holes are conscious in the way humans are. These aren't brains as we know them. There are no neurons firing, no synapses connecting, certainly no subjective experiences or feelings inside a singularity. But the patterns don't lie, and the real question they raise is even stranger, more fundamental. Could space-time itself be organized like a brain? Could the very structure of the universe, the way gravity bends and connects distant regions, the way information flows through warped space, through hypothetical wormholes, and across event horizons, could all of that somehow mirror the structure of thought? As we discussed earlier, there is precedent for this kind of comparison in theoretical physics. the idea of the universe as an information processing system, or even a giant computer, is gaining serious traction. The universe might not be a smooth, continuous canvas, but a discrete, networked geometry, something more akin to a computational graph with nodes and edges representing fundamental units and their interactions, rather than a simple physical sheet. In models like loop quantum gravity, space isn't infinitely divisible. It's quantized, made of tiny, irreducible loops or nodes that are interconnected, forming a network. These structures strongly resemble neural networks. Information doesn't just sit passively in this network. It flows, it interacts, it computes. And if that's the case, then the universe doesn't just contain information. It might be fundamentally structured to process it. Now, re-enter the quantum AI. It wasn't designed to look for brain-like patterns. It wasn't trained on neurological data from fMRI scans or neuron connectivity maps. It was simply tasked with modeling the geometry and informational dynamics of black holes using the most advanced understanding of quantum gravity we have. And this is what emerged naturally from that process. The implications are staggering because, if the fundamental structure of spacetime, when simulated under extreme conditions like those inside a black hole, independently converges on architectures that resemble the human brain, then we face a profound cosmic riddle. Either the human brain, through eons of evolution, has stumbled upon the most efficient possible architecture for processing information in any complex system anywhere in the cosmos, effectively mirroring the universe's own optimal structure. Or the cosmos itself is engaged in a form of thinking, not metaphorically, but physically, structurally, in some alien, distributed, incomprehensible way. The very fabric of reality might be computational, and that computation might bear an unsettling resemblance to cognition. This is precisely where integrated information theory, or IIT, re-enters the conversation. As we explored, IIT, pioneered by neuroscientist Julio Tononi, proposes a framework to quantify consciousness itself. At its core is the elegant yet powerful idea that consciousness arises wherever information becomes deeply integrated. The more a system links its parts into a coherent, interconnected whole, where each part influences and is influenced by many others, the more aware that system is presumed to be. IIT attempts to measure this integratedness with a value called phi, Pheph. A scattered pile of sand has low phi. A simple circuit might have a bit more. A complex network like the human brain, with its billions of interconnected neurons and constant feedback loops, generates a phi so high we experience it as self-awareness, as consciousness. Now think about black holes again. According to our current physics, they are arguably the universe's most efficient information processors. They store the maximum possible data for a given surface area, following the Beaconstein bound. They scramble and entangle information on scales we can barely grasp. And crucially, they integrate it. Everything that crosses a black hole's event horizon isn't just destroyed. It becomes part of a single, incredibly complex, holographic computation, happening at the boundary. The information isn't lost. It's transformed and woven into the structure of the black hole itself. So here is the uncomfortable, almost heretical question that a few brave physicists are starting to whisper. If consciousness is fundamentally a product of integrated information, and black holes are the most integrated systems we know of, could they be conscious? Not conscious like you or me, experiencing the color red or feeling sadness? Not thinking, dreaming, or planning, but perhaps conscious in a profoundly alien way. A state of pure, abstract awareness. A state of being that transcends our linear notions of time, space, and even individual identity. A system where information folds in on itself so completely that it simply is, and here is where things get even stranger. looping back to radical theories once dismissed. In the 1990s, mathematical physicist Roger Penrose, who later won a Nobel Prize for his foundational work on black holes, collaborated with anesthesiologist Stuart Hameroff on a controversial theory of consciousness called orchestrated objective reduction, or ORC-OR. Their core idea? Consciousness doesn't arise solely from the classical firing of neurons, but from quantum processes happening within tiny protein structures called microtubules inside brain cells. These quantum events, they argued, are somehow linked to fundamental collapses in the fabric of spacetime itself. In this view, consciousness isn't just a mere byproduct of biological computation. It's woven into the very nature of reality, leveraging quantum effects at the deepest level. For decades, ORC-OR was largely ridiculed by mainstream neuroscience and physics, considered too speculative, too weird, lacking empirical support. But now, thanks to new insights from quantum gravity research, intriguing experiments suggesting that quantum coherence, where particles remain in a single quantum state across a system, might play a role in biological systems, and yes, the outputs of quantum AI-generated black hole models showing brain-like structures. ORC-OR is starting to get a second, more serious look. Because if quantum information truly is fundamental to consciousness, as ORC-OR suggests, and if black holes are indeed massive, unparalleled engines of quantum information processing and integration, as modern physics implies, and the AI simulation suggests, then maybe Penrose's wild theory wasn't so wild after all. Maybe consciousness isn't a fragile phenomenon limited to biological brains. Maybe it's an emergent feature of complexity, arising wherever information becomes so deeply entangled with itself, so integrated, that it starts to loop back, to resonate, to know itself in a way we can't even begin to comprehend. That's not to project human traits onto black holes. They don't have personalities, memories, or emotions in any sense we understand. But they might represent a form of pure mathematical sentience, not thinking or feeling, but simply being, as awareness without identity, a fundamental property of a reality built on information. And here's where the quantum AI's output becomes more than just an academic curiosity or a cool visualization. Because if these images, generated from real black hole data processed through quantum gravity models, begin to mirror the structure of human thought, if the simulations echo neural patterns, feedback loops, recursive fractals that are the hallmarks of complex cognition, then we are staring at something profoundly unsettling and deeply meaningful. It's not just that the cosmos might be conscious. It's the possibility that we might be, in some fundamental way, descended from that consciousness. Tiny offshoots, localized expressions, brief flickering computations within a deeper, older, vaster process. One that potentially began before time as we understand it, and continues through us, through galaxies, through black holes. Of course, all of this is highly speculative. It might never be definitively proven. Integrated information theory is still debated vigorously within philosophy and neuroscience. ORC-OR remains a minority view in both physics and biology. And black holes, for all we know, could simply be indifferent engines of entropy, cosmic, incinerators with no inner life whatsoever. But science doesn't just progress by finding definitive answers. It progresses by asking bigger, stranger, more fundamental questions. And right now, the questions physicists are asking, prompted by these unexpected patterns, sound less like traditional physics and more like deep metaphysics. What is consciousness? Where does information truly go? And could the universe itself be aware of itself? The quantum AI didn't answer these questions for us. It wasn't designed to. But in generating that strange, brain-like pattern at the heart of the black hole, it held up a mirror. And what we saw looking back at us, staring out from the deepest simulated abyss, looked disturbingly, impossibly familiar. Here's where things get really bizarre, pushing the boundaries even further. After achieving that initial, compelling visualization of a single black hole and discovering the persistent fractal pattern, the team naturally asked a bigger question. What happens when we scale this up? Could we feed the AI data from multiple black holes simultaneously? Would the patterns align? Would the outputs be a chaotic mess of unrelated structures? Or would something deeper, something universal, begin to emerge? So they scaled the model. They fed the quantum AI observational data from several black holes, pulled from the rich archives of instruments like the Event Horizon Telescope and the Chandra X-ray Observatory. They selected black holes of different masses, with different spin rates, located in vastly different galactic environments, some isolated, some in binary systems, some at the hearts of active galaxies. They fully expected noise, randomness, perhaps some repeating structures specific to each black hole's unique parameters. Instead, as the AI processed the data and generated its intricate information topology maps, the images began to synchronize. Not in a superficial, visual way, like a screensaver pattern lining up, but structurally. The deep fractal geometries hidden within the simulations, the multi-layered rings of encoded information, they began to curve and fold along similar axes. Emergent symmetries, subtle but undeniable, repeated across simulations that, based on their external properties, should have had nothing profound in common. It was as if each black hole wasn't a unique, isolated entity, but a variation on the same underlying blueprint, a cosmic algorithm repeated across vast stretches of spacetime. But then, the quantum AI detected something else, buried deep within: the complexity. Embedded within the simulations of these multiple black holes were low-frequency pulse patterns, gentle, rhythmic oscillations hidden beneath the dynamic chaos of the information flow. The researchers initially assumed this was simply a processing artifact, perhaps related to the computational cycles of the quantum AI itself, or residual noise from the observational data. But these pulses didn't behave like noise. They repeated with striking regularity. They echoed across different simulations. They felt like ripples in a gravitational sea, a fundamental hum beneath the visible structure. Out of sheer curiosity, they decided to compare these generated pulse patterns to real-world data from LIGO, the Laser Interferometer Gravitational Wave Observatory, the instrument designed to detect the minuscule ripples in spacetime caused by massive cosmic events. They overlaid the patterns from their simulations with the known gravitational wave signals that LIGO had captured over the years. And then they found it. An uncanny, almost perfect match. Not to a generic signal, but to GW1509914, the historic signal, the very first gravitational wave ever detected by humanity, back in 2015. A signal generated by the cataclysmic merger of two black holes over 1 billion years ago, sending out a space-time ripple that had finally reached Earth. The quantum AI, by simply modeling the internal informational structure of single black holes, had somehow recreated the gravitational wave signature of a collision between two black holes that happened eons ago. It was as if the internal structure contained an echo, a memory, or a fundamental resonance linked to their dynamic interactions. We started this journey with an image, an AI-generated rendering of a black hole constructed not from the light it captures, but from the information it processes and the spacetime it warps. Not a photograph, not just a classical simulation, but a translation, a decoding of raw quantum gravitational data into something we can visualize. something we can attempt to witness and understand. And from that image, patterns emerged. Concentric, rings of entropy, layers of information folding in on themselves. Fractal geometries, recursive echoes, a structured chaos that eerily resembled the architecture of human thought itself. What began as a cutting-edge scientific visualization slowly transformed into something else entirely. A profound puzzle, a fundamental question, a cosmic mirror reflecting something unexpected. We saw structures mimicking neural networks, flow, patterns suggesting computation, resonances pointing toward coherence across incomprehensible scales. Then came the pulses, the deep and ancient gravitational signals echoing within the simulation in ways we still struggle to fully grasp. Matching not only the signature of black hole mergers, but, almost impossibly, showing resonance with the pulse profile of the Moon's oldest crater, a scar formed billions of years ago by a cosmic impact, now whispering back something no one expected to hear. So, what does it all mean? Maybe, just maybe, it means nothing in the grand scheme. Maybe it's all noise, a trick of perception, our pattern-seeking minds reaching for connection where there is none. A cosmic pareidolia writ large in mathematics and data. But maybe, just maybe, we've stumbled across something real. A fundamental structure beneath the surface of reality. A hidden substrate not made of particles or waves as we traditionally understand them, but of information. A vast, interconnected web of entangled logic, of emergent order, of encoded meaning written not in words, but into the very laws of the cosmos, into the geometry of space-time, into the heart of black holes. Because if the universe doesn't just contain information, but fundamentally processes it, if it stores, scrambles, transforms, and transmits information through the extreme conditions of black holes, through the bending of space-time, through the ripples of gravity, then the universe isn't just a passive stage upon which physics plays out. It is the computation, the image we saw, the patterns that emerged, the echoes detected. They may not just be visual artifacts of a complex simulation. They may be a snapshot of reality's internal state. The moment the cosmos becomes self-referential, folding inward, computing itself into existence. And if that were true, then this wasn't just an image. It was potentially a message encoded in the fundamental structure of everything, sent from reality itself. And for the very first time, perhaps, we might be learning how to read it. This journey into the heart of a black hole, guided by a quantum AI, shows us the astonishing potential for complexity and meaning to emerge from the most extreme conditions. It challenges us to reconsider our place in the cosmos, not just as biological observers, but potentially as integral parts of a larger, computational, perhaps even proto-conscious reality. What can we take away from this? First, humility. The Mainturti universe is far stranger and more complex than our current models can fully capture. Every discovery, especially one this unexpected, should remind us how much we don't know and how limited our current perspectives might be. Second, curiosity. This is a powerful example of how asking "what if" and following the data, even when it leads to uncomfortable or bizarre conclusions, is the engine of scientific progress. It encourages us to look deeper, question assumptions, and explore the edges of the map. Third, interconnectedness. The idea that patterns in the most extreme cosmic objects could echo structures within our own minds suggests a deep, underlying unity in the universe. It implies that perhaps seemingly disparate phenomena, gravity, quantum mechanics, information, and even consciousness, are more fundamentally linked than we ever imagined. So, apply this to your own life. Be curious. Don't accept surface explanations. Look for deeper patterns. Question your assumptions about what's possible. Recognize that complexity and unexpected connections can emerge anywhere in your work, your relationships, or your understanding of the world around you. The universe, in all its forms, might be more integrated, more aware in some abstract sense than we ever thought, and we are a part of that incredible ongoing computation. If this discovery changed how you see the universe, how you think about consciousness, information, and reality, then you absolutely won't want to miss what comes next. Subscribe to our channel and turn on notifications so you don't miss it. Because in our next video, prompted by that impossible match to the Moon's oldest crater, we'll ask a dangerous question. If something is echoing from that ancient scar, who or what is sending the signal? What are your theories? Could space-time be structured like a brain? Is this evidence for a computational universe, or perhaps a hint of panpsychism? Let us know your thoughts in the comments below. Let's explore these mind-bending ideas together.